Good morning, everybody, and welcome back to microprocessor course. In today's class, we are going to learn about computer classification, different classes of computers. We also have to see some computer architectures, parallel architectures. Then we'll be able to see important concept that we can use to assess our computer performance. Before we start today's class, I'm gonna check if everybody is present in today's class. Class 5, number 1, number 2, number 3, 4, 5, number 6, 7, 8, 9. Class 5, number 9. 10, 11, 12, 13, 14. Please say something. 15. 17. Class 5, number 17. 18. 19. 20. Class 5, 20. Class 5, number 20. 21. 22. 23. 24. 25. Class 5, number 25. 26. Please say something. 27. 27. 28. 29. 30. Class 6, number 1. Number 2. Number 3. Number 4, 5. Number 6. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 20, 21, 21, 22, 23, 24, 26, 27, 28, 29, 30, P21, 6, 15. Okay. Which number? All right. In today's class, we're going to talk about computer classifications. We talk about different classes of computers, parallel architectures, as well as computer performance concept. Now, let's get started with class of computers. We have personal mobile devices, PMD, and we have desktops. We have also servers, clusters, as well IoT, embedded system devices, and we have also supercomputers. So these are the important classes of computers. We have personal mobile devices. Then we have examples including smartphones, tablets, wearables, and they have important features like they are portable, and they are battery-powered devices, and they are also wireless devices. The main user cases include communication. We use them in communication using different social media applications. Then after that, we have another important class of computer, which is desktop. These include PCs, Macs, gaming computers. These have a higher performance if you compare to the previous one. We do use them in offices, and also are those kind of computers that you use for education purpose. For example, to do your research, to get access to your course materials. And we have a third important class of computers, servers. And these are important computers that are always on because they do provide services to machines called clients. We have servers. We have a server, and this is always on, 24 out of 24 hours, always on. And they do provide services to different computers called the client. 1, 2, 3, 4, and so on and so forth. So these are services getting from the server computer. That means that this class of computer needs to be always on to provide the services to other computers that we call clients. So this is an important feature of server class of computer. After that, we have warehouse computers or clusters. These are important class of computer that can help, for example, to store data in data centers. As we know nowadays, because of the advancement in technology, whenever we go out, we tend to generate data, we tend to take a picture, we tend to save our important moments. And we are texting people using different social media, so we need data centers to store our data. That can be accessed for different purposes. For example, it can be accessed to allow researchers to conduct their experiments. So we need these in cloud and big data, as well as in AI. After that, we have IoT, embedded system. We talked about this. These are tiny and lower powered, and they are task-specific devices. Last class, we talked about the difference between embedded system and general purpose computer. We have seen that embedded system is a specific computer which is designed to perform a specific task. So they are tiny, they are really small, and they are task-specific devices. User cases for IoT or embedded system, they are being used in automation and smart devices. The last one is the supercomputer. The supercomputer, these are very important computer with the massive parallelism as one of their features, as well as their speed. They are ultra-fast computers. Their use cases include simulation. They are being used in simulation to conduct research, or they are also being used when it comes to experiment by using a huge data. This is a kind of simulation as well to allow people to gain insight from huge data sets. Now, let's have a look at this class of computers, their price, the price of the microprocessor, critical system design issue linked with each of these class of computer. If you try to see for PMD, personal mobile device, these are the price of the system itself and the price of the microprocessor. The critical system design issue linked with this type of class of computer. It does include the cost. It is very expensive. And also they have another key design issue which is linked to the performance. Now, I want you to take a look at the SEVA technology, SEVA class of computer. We have critical system design, including throughput, availability, scalability, as well as energy. So we need availability for SEVA class of computer to make sure that they will be available and provide the services to our computers called the client. So availability is one of the critical system design issue linked with the SEVA computer system. Now we have clusters. For them also we have price, performance, throughput, energy, and proportionality as critical system design issues. For IoT, we have the price, energy, application specific performance. Now, we need also to have a look on the sales about this class of computers. Sales in 2015, it was about 1.6 billion of PMD. And 90% of this include cell phones. Many people are now trying to get cell phones for daily activity, for daily communication. That's why we have higher sales when it comes to personal mobile devices if you compare to other classes of computer. For PCs, desktop, we have 275 million, and for servers, we have 15 million. We see that they do contribute to the global economy because you see that they include a big number of cells each year. All right, we just finished the classes of computers. Now we're going to start with parallelism, different parallelism architecture in computer system. We know that we have a limited speed for serial processing, for sequential processing. If you only have a computer which can perform, which can execute a task one after another, this will limit the computer performance. So we need to talk about some important parallelism architecture to solve this issue. But we have learned about Moore's law, which made available enough transistors, enough computer components to do more execution with parallel hardware on the same processor chip. We talked about many cores on a single processor chip to allow many threads to be executed at the same time because each core will be able to handle a thread at its own. That's why Moore's law has made available enough transistors to do more execution with parallel hardware on the same processor chip. So we have this parallelism architecture which include single instruction, single data. That means that this instruction only needs one data stream to be completed. That's why we have one-to-one. We only need one data stream to complete this instruction. We have single instruction, multiple data. That means this instruction requires many multiple data to be completed. We have one too many. That means this type of instruction requires many data streams to be completed. One too many. For example, if you have a picture in image processing, if you have a picture, it does include many pixels. And to be able to identify what does this picture represent, we need to get to know what does these all features, these pixels of the image represent. That's why we need one-to-many. One instruction applies to many data streams to get to know what is this feature. So many, one-to-many in image processing, for example. Single instruction, single data is like a simple calculation using your computer. Let's say you are doing addition, 5 plus 3. This is a single instruction, single data. Now we have single instruction, multiple data. We are applying a one instruction to multiple data stream. The third parallelism architecture is multiple instruction, single data. Multiple instruction, single data. We have multiple instructions, many to one. That means we have multiple instructions. Those instructions require only a single data stream to be computed. For example, in tolerant system, so we need a single data to complete a multiple instructions. So the last one is multiple instruction, MI, multiple data. That means many to many. We have many instructions, and those instructions require many data streams to be completed, many to many. These are very important in multi-core CPU system. When we have many instructions that need many data streams to be computed. So we have these four parallelism architecture. Single instruction, single data, when you are doing a simple calculation using your computer. We have single instruction, multiple data stream. For example, in image processing, we have multiple instruction, single data. In tolerant system, we have multiple instruction stream, multiple data stream. So to summarize this parallel architecture, Fanny has provided this taxonomy. We have single instruction pool. We have a single instruction pool, which only needs a single data pool to complete this instruction. We have a single instruction from the instruction pool, and we have a single data stream to complete this instruction. The second parallelism architecture is single instruction, multiple data. You see, we have a single instruction which comes from the instruction pool, and we need multiple data streams to complete this instruction. This is single instruction, multiple data. We have many instructions, 1, 2, from instruction pool, which only require a single instruction data stream to be executed. The last one, we have multiple instructions from instruction pool, and multiple data to complete this instruction. So we have four parallelism architectures. We have the description, single instruction, single data. We have a system example, task example. For single instruction, single data. System example, we have a single core CPU. Then task example, we have a simple calculation, a simple operation. For single instruction, multiple data, we have GPUs. As I said before, one of the tasks is image processing. Multiple instruction, single data, we have many instructions on the same data. So this is a rare parallel architecture in the computer system, but they are being used in real-time error checking, for example, in aircraft control, as well as if you need to validate the data during the experiment. The last one is multiple instruction, multiple data stream. We have multiple instruction on multiple data independently. So system example, we have multiple CPUs, and use case examples, we have learning multiple applications, all parallel simulation. So this is the full parallel architecture with the system example as well as use case example. We have applications which exhibit two types of parallelism. We have data level parallelism, DLP. What does this mean? It means that we have multiple data items. These data items can be processed at the same time. Data level parallelism. Many data items which can be processed at the same time. The next one is task level parallelism, TLP, means that we have independent tasks that can run largely in parallel. Task level parallelism means that we have different tasks and the task can be handled in parallel. We have first one, we have DLP, data level processing, and we have TLP, different tasks that can be independently run in parallel. When it comes to hardware exploitation, we have four ways. We have instruction level parallelism, and we have also multimedia architecture. That means a single instruction are being applied to multiple data items in parallel. We have three-level parallelism. This includes data level parallelism or task level parallelism in tiny capped thread with different interactions. The last one is request level parallelism. We have independent tasks, and those tasks are being executed in parallel. And this is being managed by what we call operating system or the programmer. So we have these four hardware exploitations: instruction level parallelism, vector architectures or GPU architectures, and phase level parallelism, as well as request level parallelism. So we are with parallelism. We just talked about four parallelism architectures, including single instruction, single data stream. We talked also about single instruction, multiple data stream. We also talked about multiple instruction, multiple data. And we just have talked about the DLP, data level parallelism, and task level parallelism. And we have seen that for data level parallelism, there are many data items that can be executed in parallel, and the task level parallelism, we have seen that these are different tasks that can also be handled in parallel. Now, if there is no question, we're going to start the important topic in the computer performance, how we measure the computer performance. How can we assess our computer performance? We need the relative performance, clock speed, number of instructions executed per second, or we need latency, throughput. We need clock speed. So this is some important computer performance concept that we are going to talk about in this class. So let's get started with computer performance, relative performance. Relative performance. Now suppose you have two computers, computer A and computer B. If computer A runs a program in 10 seconds, and a computer we have two computers, two different computers, computer A and computer B. If a computer A runs a program in 10 seconds, and the computer B runs the same program in 15 seconds, so which computer is fast? Which computer is fast? So our computer A runs a program in 10 seconds, and the computer B runs the same program in 15 seconds. So which computer is faster between computer A and computer B? Which one? We have a program, and we have two computers. We have a computer A, which runs the program in 10 seconds, and the computer B runs the same program in 15 program. How much faster is computer A to B? So we need to get to know how much faster is computer A to computer B, because we have seen from the description that our computer A is faster because it runs the same program in 10 seconds, whereas the computer B runs the same program in 15 seconds, which means our computer B requires more time to execute, to handle the same task than computer A. So we need to know how much faster our computer A is. We have performance. Performance of computer A divided by performance of computer B. That is execution time. Execution time for computer B divided by execution time for computer A. Then we have how many times our computer A is faster than B. So execution time for computer B is 15 seconds. Execution time for computer A is 10 seconds. Thus, our computer A is 1.5 times faster than computer B. So this is what we call relative performance. We needed to know how many times does a system A is faster than a system B. We take execution time for the system B divided by execution time for the system A. Now, clock rate. We also need to talk about clock rate, clock speed. So we need to make sure that we understand what is a clock speed. Clock speed is like oscillation, physical oscillation of the frequency, CPU frequency. So this is about hardware. When we talk about clock rate, it's more often the same, but it is used in performance and the analysis. For example, you see here, we have improvement in clock rate starting with, from 1978 and 1988. You see that we had a 15% per each year improvement in the clock rate. It was 5 megahertz. As you can see, there was increase in clock rate between 1988. We had 1988 and 2003. We had a 40% improvement per each year, and you see it was starting from 16.7 megahertz. So in between 2003 and 2017, you see that we had only 2% improvement per each year. So there was a big improvement in the clock rate. CPU clocking. So because we are talking about clock rate, we need to make sure that you understand what it does mean, the clock period and the clock frequency, or the clock rate. So each task in a computer system requires what we call clock cycle to be computed. So we're going to talk about how many clock cycles does each task require to be computed. For example, you see here the clock period is the duration of each clock cycle. Clock cycles are required for each task to be computed by a computer. So which means we need to know the duration of each clock cycle. It's going to be in second, picosecond. This is one of the examples. We have also clock frequency. These are the number of cycles per second. Number of cycles per second. We have, for example, 4 gigahertz, and you see how much it does equals in megahertz and so on and so forth. So make sure you do understand the difference between the clock frequency and the clock rate. Each task needs a number of clock cycles to be completed. Thus, we needed to know how much time is one clock cycle. That is what we call clock period. So we also needed to know what is the clock frequency, cycle per second. So there is a glow in processor performance. This picture on the screen depicts the performance in processors starting from 1978 and 2008. To summarize this, you see that starting from 1978 and between 1978 and 1986, we had 25% improvement in processor performance. And we're going to see what was the reason. The reason was technology improvement, more transistors on a single processor chip. And between 1986 and 2003, we had a 52% per each year. And this was due to the RISC architectures as well as pipeline. Pipeline means when we have many cores on a single thread, each core is able also to perform different cores, and will be able to execute many threads in the same clock cycle. Pipeline, we're going to talk more about this pipeline technique when we'll be talking about instruction clock cycles, instruction cycles, instruction fetch, instruction decode, execution, memory access, and the write back. From 2003 and 2011, we had an improvement of 23% per each year, and it was due to many cores on a single processor chip. And from 2011 to 2015, as you can see, we had only 12%. 12%, why? Why 12% is because there was the problem of parallelism limit. Amada is low. We have a number of tasks that need to be handled by our computer system, but we needed to understand that even though we have many cores on a single processor chip, not all tasks that a computer has on his hand can be done in parallel. Some tasks require to be handled in serial, in sequential manner, one after another. That's why there was parallelism limit. And from 2015, we had till 2018, we had a small growth in the processor performance. That was 3.5% per each year, due to more is low and physical limits. We have seen that more is low says that the number of transistors would double every 18 to 24 months. But we have seen that there is another problem, a key issue of power consumption. we needed to make sure that those transistors that we are trying to add on a single processor chip, we be able to power them on. So there is a problem of limit of Moore's law, because we need also to make sure that we be able to power those transistors. Another key issue is in mobile devices. Mobile devices, because we have to take into consideration about battery life, because these types of devices are portable. They need to be used when they are not charging as well. So we needed to make sure that we add more transistors, but those transistors won't be able to keep our battery in good life, to use it as much as possible. So we just talked about the growth in processor performance. Now we're going to talk about some important computer architecture concepts which can help us to assess computer performance. Now, starting with million instructions per second, MIPS. This is a basic measure of CPU performance. We have to represent how many millions of instructions a processor can execute per second. How many million instructions a processor can execute per second. Million instructions per second, MIPS. MIPS. We have million instructions per second equals to instruction count divided by execution time times 10 to the power of 6. Or if you are using the CPU parameters, the MPIS, million instructions per second, equals to clock rate divided by CPI, cycle per instruction, times 10 to the power of 6. So the clock rate need to be in hertz. Million instruction per second is a basic measure of CPU performance, and it represents how many million instructions a processor can execute per second, and it is given by this expression, instruction count divided by execution time times 10 to the power of 6. Now, we have a good example on how we can calculate million instructions per second. We consider the following performance measurement for a program. We have measurement for computer A and the measurement for computer B. We wanted to know which computer has the higher million instruction rating and which computer is fast. So we have instruction count for computer A, we have clock rate for computer B, we have CPI for computer A as well and B, and the CPU time. So I want you to tell me which one has the higher million instruction per second rating. Please, you have 2 minutes to complete this. Hello? Are you there? You have 2 minutes to complete this exercise. Tell me which computer has a higher million instruction per second rating. Hello, everybody. Please, you have 2 minutes to complete this exercise. So which one? Which one has the higher million instruction rating? Computer A? How many? 4,000. So you have million instruction per second for computer A. That is instruction count, how much is? 10 billion, right? 10 billion. Execution time for computer A is 2.5 times 10 to the power of 6. That is 4,000, right? Then you calculate million instruction per second. For computer B, we have 80 billion as instruction count divided by execution time for computer B, that is 2.2 seconds times 10 to the power of 6. How many here? How many million instructions per second for computer B? Huh? 3,636. Thank you. Now, you see that our computer A has higher million instructions per second because it has 4,000 million instructions per second, and our computer B has only 3,632 million per instruction. So this is A. B, which computer is faster? Hello? Which one? A or B? B? A? B? A? Huh? Why? Huh? Yes, very good. Now, because we see, even though our computer A has higher million instructions per second, it doesn't mean that it is really fast. Because our computer B has CPU time of 2.2 seconds, and our computer A has 2.5 seconds. That means our computer B is faster than computer A because of the CPU time. The CPU time shows you which computer is fast between these two computers. Thus, our computer B is faster than computer A, even though computer A has higher million instructions per second rating. Our computer B is faster than computer A. Very good. This is your 5-minute break. Please take your break.